Okay, so I admit I've done this before, but I'm going to go through how to model the motion of the space station. Oh wait, this is actually a video. Model the motion of the space station in Python. Okay, so this is the actual live view of the space station. And I've already derived orbital motion, and I'm going to make this even better, but right now I just want to get the basic stuff down. Okay, so let's go through some of the basic physics. This video is from NASA. So let's just don't worry about that. Okay, so let's start with the main starting ideas. Number one, this is what you need to know. Universal gravitational force. If I have two masses that are attracted to each other, I can calculate this as a force. It depends on the product of their masses. It depends on the distance between them, r. And then if I want that unit vector, I need that unit vector in there to make it a actual vector force. And we're going to do that. I'm going to show you how to do that. Okay, then we have the centripetal acceleration. So if an object's moving in a circle, if we want a circular orbit, then the centripetal acceleration is going to depend on the magnitude of the velocity. This is the magnitude of the centripetal acceleration, v squared over r, or we could write that in terms of the angular velocity, omega squared r, and we'll do it both ways. Next, Newton's second law. Now, in the past, I would do this using the momentum principle. I kind of like that better, but most introductory courses start with Newton's second law, F net equals ma. So I'm going to do it with F net equals ma, so it will be a little bit different than the way I've done it before. This just says if you know the net force on an object, then you can calculate its acceleration, and that's what we're going to do. The definition of acceleration. So if the acceleration is constant, then the acceleration for some time interval delta t is just the change in velocity divided by the change in time. It's the rate of change of velocity. We don't even need to write this as a derivative. We could just write this as a finite difference, delta v over delta t, and that's what I'm doing. And then finally, the definition of velocity. This is technically the definition of average velocity. It's the change in position. We use the position vector r divided by the change in time. Let's see. Oh, I want to put my thing up here. Where is that? Okay, well, I don't have my... That's fine. We'll do it live. Okay. I'll back down here. So, imagine that we have the Earth, or some Earth-like planet, because I didn't draw the continents correctly, but it did put an ice cap, so maybe that's not completely accurate. That was a bad joke, I know. Okay, and then I have some satellite. Yes, it's giant, but you won't be able to see it. It's right here at some position R1, and the 1 means just in terms of time. And that's measured from the center of the Earth to the center of the satellite. It's a vector, though. That means that there is a gravitational force in the opposite direction as R1 on the satellite. And I could calculate that using the gravitational force, which I will do. And now this object has some velocity. At this instant, it has a velocity vector, v1, in that direction. Okay, so now here is one small point. R1 isn't necessarily the position of the satellite. It's the relative vector from the Earth to the satellite. So now if I put my Earth at the origin, the center of the Earth is at the center of my origin, that's fine. Then R1 is the location of the satellite. Otherwise, I need to calculate that. So if the Earth is not at the origin, then I need to find that. It's really just the position of the satellite minus the position of the Earth, and that will give the relative vector from the Earth to the satellite. And I'm just putting that out there so that we can use this. I think it's a good idea to do that. So that if you have more than one object moving, it's going to be important that you do that. Okay, so now imagine that some time interval happens, some change in time delta t. And at the end of that time interval, I have the objects moved. It's at a new location relative to the Earth, R2. It has a new velocity, it has a new gravitational force, Fg. Okay, I didn't put them Fg1 and Fg2, I'd call it Fg. But it has a new velocity. And so what we want to do is to be able to find that new velocity, find that new position after the short time interval. And this is the key thing, small delta t. We're going to make the assumption that we have a short time interval so that we can make some assumptions. So here's how I'd calculate the gravitational force. If I take the gravitational constant g, the mass of the Earth, which I use capital M, the mass of the satellite, lowercase m, and I divide by that r vector magnitude. Now, if I did that, I would have the scalar value. But if I put in the negative and the r hat is a unit vector pointing in the direction of the position vector, the relative position vector. And so that will turn this back into a vector. The negative sign means it's an attractive force. Okay. With that, I can calculate, using Newton's second law, I can calculate the acceleration vector. So the acceleration is the net force divided by the mass of the satellite. And so I get the acceleration as one step. I could. I'm not going to do it that way. I'm going to calculate the force and then I'm going to divide by the mass, which seems dumb, but that's what I'm going to do. But if I assume that during this time interval, the acceleration vector, not just the magnitude, but the vector is constant, then I can say this. Then I can say the velocity at the end is the velocity at the end, the beginning, plus the acceleration times dt, delta t, right? That is the kinematic equation for constant acceleration, which is not constant. I mean, if this object moves over here, it changes distance, it changes direction. The acceleration is not constant. But if delta t is small, it's not bad. So the key is we want to make delta t small enough that that's a fair assumption. Now, I can also assume, even though the velocity is changing, I can assume the velocity is constant. When you're like, well, come on, man. You can't do that. You can't assume acceleration is constant and velocity is constant. It just doesn't make sense. I get it. It doesn't make sense. But it works. Okay. If you assume the velocity is constant, then I can assume the velocity, the average velocity during that time interval is the final velocity. It's close to being the same. And then I can do the same thing for the kinematic equation with zero acceleration. Final position, initial position plus initial velocity times delta t, but I'm using the final velocity, okay, because I just calculated that. Okay, so that's our plan. If we do this for a short time interval, I can do it again for the next time interval. I can do it again for the next one after that. So I can just break this into a bunch of small time intervals and just keep doing this for as long as I want and model the motion of a spacecraft near the Earth. Okay, so I want to do this for the space station. So we need some values. The mass of the Earth, this is just a constant, 5.974 times 10 to the 24th kilograms. The radius of the Earth, we only need that because I need the distance from the center of the Earth to the space station, and we usually list the space station's distance as an altitude above the Earth. So we have 6.371 times 10 to the 6th, and then it's 400 kilometers above that. So I know you could just say R and add it, but I didn't do that. And then we have the gravitational constant, G, 6.67 times 10 to the negative 7th. And then I'm just going to try a delta T of 100 seconds. Okay, I think I'm ready. I lost my, let's see. I think the next one, yeah. Okay, so let's just jump into Python and do this. So I'm going to switch over here to Python. Okay, so I am using GlowScript WebVPython. This is I'm actually using it in Trinket because it shows the code side by side, and I can let you use it. You don't have to log in to edit it. This is a web-based version of Python with some really cool features in there with 3D objects and things like that, and I'm going to show you these 3D objects. You're going to love them. All I've done so far is just enter in my constants that I already said, right? So I have G, M, E, R, E, H, T is 0, and DT is 100. Now, you'll notice that I don't use units because these are numerical calculations. I need to deal with the numbers. If I put a unit there, it's no longer a number. This is Python. It's not real, right? It's just Python. So let's do a couple things. I want to make the Earth, and I want to make the space station. So let's make the Earth. So I'm going to say Earth equals sphere, position equals vector 0, 0, 0. So when I make a sphere, we can give it a couple properties. We can give it the position of the center. We can give it the radius. We can give it the color. I'm going to actually give it a texture. Okay. So I'm going to put it at the origin. And then I'm going to say the radius of the sphere is RE, which is giant, but that's fine. It's going to zoom out. And then I'm going to give it an Earth-like texture. Texture equals textures dot Earth. And let's run it and see what happens. There you go. The Earth. And so this is a 3D Earth. You can rotate that around, and I think that's pretty cool. Now, in a future video, I'm going to make another video. I'm going to take this, I'm going to rotate the Earth, I'm going to make it rotate like a day, I'm going to make it look more realistic with correct lighting and stuff like that. But for now, let's just leave it as it is. And you can change that. But it does look like the Earth. And you can zoom in and zoom out. This is what makes WebVPython so awesome, is that it has these three-dimensional objects that are fairly easy to make. Okay, so there's my Earth. Let me show you. I can do stuff like this. Print earth.pos. That's the vector location of the Earth, because we could use that. And so it printed out 0, 0, 0, which is what we knew. Okay. Now let's make the space station. I'm going to call it ISS. And it's also a sphere. Where is it going to be? Well, I want it to be, let's say, on the x-axis, a distance r away. So let's say the position is going to be vector re plus h, 0, 0. Now, what about the radius? If I make this the radius of the space station, let's say 200 meters even. Let's just put that. 200, and I'll leave it blank, the color, so that'll make it just white. But I will do this, make trail equals true, and let's run this. It's not moving or anything, it's just going to be sitting there. Oh, let's see, I'll click down here. Okay, so it's right over here, but you can't see it because it's just too small. So let's go up here and make the radius, let's say RE divided by 20. Let's see if we can see it then. There it is. There's the space station. Way too big, but that's that. Okay, so let's make it a little bit smaller, but that's fine. Let's make it 40. Okay, so now we do need a couple other things. I do need the mass of the space station, and I'm just going to pick this. I'm going to say ISS.m. You can assign a property to the object ISS, which I named it myself. So I can give it a mass. Let's just say it's 1 times 10 to the 4th, 10,000 kilograms. It doesn't really matter. I also need to give it an initial velocity so that I can calculate the change in velocity. So I'm going to say this, ISS.v equals vector. Let's just make it move in the positive y direction. I'm going to give it a velocity of, let's say, 3,000. I'm just picking something here. Honestly, I don't know what it's supposed to be. 3,000, 0, 0. So I know the velocity to start off with. I need to know that because at the end of the time interval, I'm going to calculate the velocity based on the velocity at the beginning of the time interval. So I need to know the starting position, which I have. And I need to know the starting velocity. Let me show you also print ISS.pos. That's the R vector for the space station, right? I don't need to say R space station. I just need to say that. So that's where it starts off. Okay, so I think we're ready. Let's go ahead and say while t is less than, how long do we want to run this? Let's say I'm doing 100-second steps. So let's say I run it for 1,000 of those. So let's say, I'm just guessing here. So 1,000 times dt. Now I'm going to say this rate 100. I think that might be too, that's fine. So rate 100 says don't do more than 100 calculations per second. I do not want this to run in real time. If I had it run in real time, it would take 90 minutes to go around the Earth. Nobody got time for that. I don't have the patience to run that, so I'm not going to do that. So I'm going to run it faster, and you can change this up, and we may change that. Okay, so the first thing I need to do is to calculate that gravitational force on the space station. But to do that, I need to calculate the vector r. So this is a redundant step, but I'm going to say r equals ISS.pos minus Earth.pos. Right, so ISS.pos is the vector location of the space station, and Earth.pos is the vector location of the Earth, and so that's going to be a vector pointing from the Earth, from the center of the Earth to the space station. And yes, the Earth.pos is 0, so it would be the same thing. But like I said, if you move the Earth, this calculation still works. Okay, so the next thing I'm going to do is calculate the gravitational force. This is actually the net force because there's only one force acting on it. So I'm just going to call it F, and I'm going to say negative G, I got that up there, times ME times, I'm going to write it out, ISS.m, right, even though it's going to cancel, times norm R. So norm is a built-in GlowScript Python WebVPython function that returns a unit vector in the direction of that vector. And now I'm going to divide that by mag r squared. So mag is also a built-in function that returns the magnitude of a vector. So I don't have to do that manually. It's built in. And then I square it. Square in Python is star 2. And I do the magnitude last just to make sure I get my order of operations correct. So then I have the force. Now I can calculate the acceleration. I'm actually going to write it like this. ISS.A equals F divided by ISS.M. It's just good manners. That's good manners right there, right? That says I'm going to assign that acceleration as a property of the object. It's the object's acceleration. Okay, what was the next step? The next step was to use that and to update the velocity. So this one looks a bit weird. ISS.V equals ISS.V plus ISS.A times dt. So this looks weird because it looks like ISS.V cancels right here, but it doesn't. This is not an algebraic equation. This is a make equal to operation. This says take the velocity right here, add acceleration times dt, and then make that the new velocity. Okay, so it's a velocity update formula. So this is V1, and that's V2. And then the next time I go through the loop, that will be V2, and that will be V3. So I don't need to keep track of a billion different variables. I just change the value of the velocity. I need to do the same thing with the position. ISS.POS equals ISS.POS plus ISS.V times dt. That's that velocity update formula. And then finally, I'm going to update the time. T equals T plus dt. Okay, and I don't know if this is going to run. I probably made a mistake. Like to make mistakes. Going to save it. Let's just run this. And again, I didn't plan this out beforehand, so it might fail miserably. Okay, so that's fine. Something bad happened. It blew up. Why did it do that? R, negative G. Let's run it slower. DT, maybe DT is too big. Let's run it like this. Maybe we can see what's happening. Okay, I know I did it wrong. Yeah, okay, so it's working. In fact, I did not launch it this way. I launched it that way. So what happens is it goes away from the Earth, falls back into the Earth because the Earth isn't really there, and then it goes through the center of the Earth. And when it does that, the gravitational force gets ginormous and it gets shot out. So let's change this velocity and make it in the y direction. There, that's better. And then dt is, let's change that back to that, change that back to that. So now it's in the y direction initially, and that's important because remember, I'm starting on the x-axis. I want to start in the y direction. Okay, so it again, I think it's got launched. Let's just try decreasing the time step to 50 and making this 500. Let's try that. Okay, so it's still doing it, right? It's going through the Earth and it's getting too close. So let's just make this a little bit faster. I'm just going to say 7. Okay, so now there we go. It's going through the Earth still. You see, so what's happening is it actually is orbiting the Earth. It's not a circular orbit. It goes into the Earth because it doesn't care. There's no Earth really there. And then let's just do one more. Let's put this at 10. And then we're going to calculate the best value in just a second. So there you go. So it's working. That's working. And that's awesome. You can rotate this around. I'm pretty happy with the times. I'm pretty happy with everything. That's not a circular orbit, though. So how would I get a circular orbit? So let's go back to this. Oh, there's my link. I didn't have my notes. Okay. So here's the Earth. And here's the satellite or the spacecraft, or this space station, in a circular orbit. So I know that this has a radius of r, and the spacecraft's moving at a constant magnitude velocity v. If that's the case, I can set Newton's second law for this situation to say the net force in the r direction, which is pointing towards the center of the thing, it changes, right? So my axis changes. I'm just making that as an easy way. So the acceleration is also in the r direction. the net force is, and this is just now a scalar equation because I'm only dealing in the r direction. The scalar force is g_m_e_m over r squared, and the acceleration is mass times acceleration of v squared over r. So now all I need to do is to solve for the magnitude of the velocity. The masses over here cancel. One of those r's cancel right there, and then I take the square root. So I get square root of g_me over r. That's that. Okay, so let's do that. Oh, let's see, what did I do? Okay, there. So I'm going to go over here, and I'm going to calculate v. Let's say v 0 is going to be the square root of g times mass of the Earth divided by RE plus h. Because that's the initial position. That's the initial distance. And then down here, I'm going to say v0. And now I'm going to run it. And you'll notice that it is indeed a circular orbit. You see that? It comes back to itself. It stopped over here. And I've done this program, so it doesn't really matter where you put your space station. I can increase the altitude to, let's say, 900 kilometers. And everything will work. So I dealt with it in terms of h. So this is your weird orbit because it's a polar orbit. Why would you do that? But it is there, right? And this is indeed awesome. Let's make it a little bit higher even, 1500. I'm pretty happy with that. Cool. Okay, so I'm going to give you a link to this code down below. If you want to look at circular motion for orbits and stuff like that, I have another video on that too. I'll link that down below. And then I will make another video where I make this more realistic, so we can change the lighting. We can make look like there's a sun and half the Earth's in dark. We can make the Earth rotate. We can do all that stuff and have fun. Because that's the nice thing about WebVPython is that it is kind of artistic, right? This is cool stuff, and I like to play with it. I find that students like to play with it too, so I will show you how to do that in another video, but that's that for now.